Gut, herzlich willkommen, meine Damen und Herren, wieder zurück zum nächsten Teil unserer Veranstaltung. Herr Eichelberger hat es vor der Pause schon angedeutet. Wir werden jetzt umschalten in die USA. Von daher wechsle ich auch direkt die Sprache. Welcome, Christian Kästner. I hope we see you in your video. Okay, great. Thank you very much that you agreed to participate in this meeting, in this workshop. So we have several people here live, and we also have a few people online. And it's great that you agreed to do a presentation here for us. I personally know Christian for quite some time because we have some research background, some common research background in the area of product lines, but this will not be today's topic. The reason why Holger and myself asked him whether he would be willing to do a presentation today is because he is, over the last few months, years, roughly, more and more into software engineering and AI. And then we thought, if we are doing a presentation, a workshop like this one, there's one guy we would love to have, even if he cannot come in person. And so we are very glad that you will be here today with us. Christian Kästner.
All right. Can you hear me okay?
Yes.
All right. Thanks for the invitation. So I want to talk about how all the difficulties that come from kind of productionizing machine learning projects. Anyway, so I want to talk about kind of productionizing machine learning systems and the challenges that come with this. And you already mentioned a little bit about my background. I come from a software engineering background. I've done research on product lines and open source. And I got to into this area of how does software engineering change if you start using machine learning components, mostly out of a teaching curiosity and necessity. We have a lot of students, both undergraduate and master students that specialize in software engineering, and a lot of them go out into the world and they will build some products that have machine learning in them. Apps, cars, web services, all these kind of things, and we don't really teach this. So they can take a machine learning course, and most of them do, and we teach traditional software engineering, but what changes at the boundary? And this is what I want to talk about, and a little bit about how we can foster more integration there and more collaboration. So the idea here is really building and operating software systems with machine learning components. So not just building models, but building systems, and doing so with interdisciplinary collaborative teams where you have both the data scientists that are specialists in machine learning and people skilled in software engineering. Right? So I want to move beyond just building models, what often happens in a notebook and in the classroom and how we often teach machine learning, to building actual software systems. Take, for example, Microsoft PowerPoint. That's clearly not a machine learning system traditionally, but they started putting machine learning in. For example, there's this design idea feature in recent versions, which you can click, and it uses machine learning in the background to make some suggestions how to improve your slide. Something I obviously didn't use for mine, but it's kind of a big traditional software system where machine learning plays a small role, but it's an important component and we need to account for it in the system design. Another very common example is cancer prognosis, where you take images, CT scans or similar things, and the background of a person, the medical records, and you try to predict, is there cancer in the image? You try to help practitioners. And again, there's a lot of research on this in machine learning conferences and so on, where it's really focusing on how can we get from a model to from data, from images, labeled data, to a model that gives good predictions. But in practice, you really need to convince radiologists and other practitioners to use this. You need to integrate this into a medical information system. Just use an open source thing here to stand in for it. But there is a larger software system that you kind of need to think about. How does a machine learning component fit into this system, how to integrate it, and so on. And my last example, and one that I'm going to use a lot in this talk, is the transcription service. So think about, you did some research on how to get from audio to text, something that's used for subtitles. We use this a lot in our research when we interview people and we need the text of the interviews afterwards to analyze them. So this is a big market, and there's a lot of research on how to do transcription well or automatic subtitling well. But again, you want to build a product around this if you actually want to productionize it, right? So that's what I'm interested in here. We have, and this is Thema, a screenshot from Thema, one of the companies in this space. So you upload an MP3 file, you pay with a credit card, and there's the transcription model, the machine learning model is clearly the core of the system. That's the key part where most of the innovation is, but there's lots of other engineering things that we need to think about, how to do the front end, how to do the database storage and processing, how to do credit card payment. And so if you think about this as a whole system, you have all these different components, and speech recognition or transcription, the machine learning component is one of many components in the system. Clearly a really important one. Without this, we wouldn't have a product. In some cases, in some systems, it's more or less important. Here, it's really important, but still, there's other things around it, and we need to start thinking about how to integrate this. And to be honest, it's not just one component, but we have the model, the speech recognition model, but we also have the pipeline that we use to build the model, probably repeatedly because we need to update it. We have some monitoring component, right? So we have multiple components that relate to these machine learning systems and that kind of integrate with the rest of the system. Like, it's easy to clip kind of newspaper headings, but there's lots of these claims that it's really hard to go from a model into production. Like modeling something, there's a bunch of projects that fail in the modeling stage, but then putting those into production, actually building a product around it is really hard. And a part of the challenge here is that we have people with different backgrounds that we need to bring together. And I'm going to oversimplify in this talk and mostly focus on data scientists and software engineers. But these are people with very different specialties, with different educational backgrounds, and we need both of them to bring them together. And again, I'm going to oversimplify here, but this is our definition at Carnegie Mellon of software engineering. And the key focus here is software engineering is more than just programming, right? It's kind of thinking about the system, thinking about many different qualities like cost, correctness, performance, scalability, security, maintainability, and so on. And typically you can't have all of them. You don't have all the money in the world or the time in the world. You need to make design decisions, trade-off decisions, need to deal with incomplete information. So this is all about engineering judgment. In our master's program, we have this running joke that pretty much every question that we ever ask in a class, you can answer, it depends. But the mark of a good software engineer is that they don't just say it depends, but if you give them a specific problem, they can figure out, oh, in this specific case, I would recommend X because of this. So they can analyze the problem and make an engineering judgment and a recommendation. On the other hand, and again, I'm oversimplifying and probably offending a couple of data scientists here. The way that we teach machine learning and the way that most machine learning research happens these days, it's focused narrowly either on the modeling technique, how can we build better deep neural networks, or on building models. So in a class, you might give students a data set like Titanic, and then you do feature engineering and data cleaning and build the most accurate model that you get. You evaluate it on accuracy, and then you're done. There's pretty much nobody deploying something, maintaining something, paying attention to drift. In research, a little bit more, but even there, machine learning research focuses on the modeling part, less on deploying and actually maintaining and building products. So what we have here is data scientists and software engineers with different backgrounds. They come from different educational backgrounds, we teach them differently, and they focus on different things. They might overlap, right? Again, I'm oversimplifying here just to make a point, but data scientists tend to be working with fixed data sets, focus on accuracy, focus on the modeling and feature engineering, and software engineers are much more concerned about cost and stability and release time and things like this, and designing a system that works. Not that one is better than the other, right? They both are really important for building these systems, but we need them both. For example, here in this transcription example, we need data scientists to build the model. This is really the key of the business, and this is not what you would expect a typical software engineer to be able to do, right? So you need somebody who knows about the modeling techniques, about the neural networks, about the challenges there, and the techniques, and stays up with the literature. But you also need somebody to build the front end, to build the back end, to take credit card payments, and to keep the system running and actually make it scale if you have hundreds or thousands or millions of users using it. For example, if you want to use this to live subtitle television programs or things like this, or talks like this. Right. So in this talk, I'm planning to talk a little bit about how does machine learning, how does software engineering change with machine learning? And I think you've heard this earlier today, although it was a little bit early for me to join all of that. Then I want to talk more about how we should move from our reasoning from models to systems. And then last part, I want to bring it back to teams. So what's actually different when we have machine learning? Let me go through some of them. So in traditional software engineering, some of our key principles are abstraction, reuse, and composition. So we build software with divide and conquer strategies where we decompose a system into components, components into functions, and we can typically say what each of those things are doing. So here's a function to compute deductions in a text software. Don't ask me about details, but there's some specification of what this function is supposed to do, right? So this is also how testing works. We give some inputs, and if it doesn't give us the expected output based on the specification for any of the possible inputs, we would say the system has a bug and we better go and fix it. We can push this a little bit further and do kind of formal specifications. So in practice, people don't really do this, right? For square root, we could define what it actually means. And divide and conquer is really important to actually scale and be able to build on abstractions and actually build larger software. This is how we enable working with teams, that we can divide work. We have an API or an interface between the teams that we can agree on, so they don't need to talk about each other with each other all the time. Right? And we can test these components against their specifications, at least to a large degree. With machine learning, this changes. And this is, I think, one of the most fundamental changes from a software engineering perspective, that we don't have a good sense of specifications. We don't have any specifications beyond transcription takes an audio file and gives me the text that's in the audio file. But we can't say how this works. We've tried this, we tried to do transcriptions for many years to figure out, oh, if we see this waveform or these vocalizations in a row, that's maybe this word. It got us some far, but we got much, much better by changing perspective and not trying to explain what's actually happening, but learning from data. So just figuring lots and lots of examples, let the machine figure this out itself. But what we're getting back, the model in most cases, and especially in transcription, you have a deep neural network with millions of parameters, and we have no idea what's going on. So it becomes actually really hard to figure out what's right here. Even humans might not agree what the right transcription is for an audio file. Cancer detection or recidivism prediction, all these are hard problems, and we use machine learning specifically because we don't have a specification. Right? We wouldn't use machine learning for the text example or for a square root, because we have specifications, we know how to do this. We can program this without machine learning, but if we go into this area where machine learning really excels, vision, audio, NLP, right? Those are things where we don't have specifications, and because of this, it's really hard to talk about what does it mean to be correct. Right? So what's a bug in a transcription service? What's a bug in a cancer detector? And I think here one key shift is important. And I find this quote very useful. It's very well known. All models are wrong, but some models are useful. This is like from the 60s in statistics, but the same idea applies here. Machine learning models are never truly correct. We don't even know what correct means. We're happy when they make good predictions that we expect, like 95% of the time, maybe 99% of the time. Sometimes we are happy with 60%. We accept that machine learning models will sometimes make wrong predictions. Nicholas talked about the long tail distributions, right, where we have some special cases and we may not handle them. But not even special cases. We sometimes have fairly normal cases or brittle cases where we don't understand why a model makes a wrong prediction. And we don't fix one wrong prediction at a time. That really wouldn't get us anywhere. What we should ask much more than, is this model correct? Which doesn't have a meaning because we don't really know what correct means for most of the time. We only have examples. We should ask whether the model is good enough for a particular application, right? Is it good enough? Is the risk low enough? Is it useful? Does it give us good transcriptions most of the time? Things like this. And you can see this in lots of other places. So, for example, Newton's law of motion is kind of a model that we learn from observation about how gravity works and how objects move. And it's wrong. It works really well for a lot of observations, has been repeatedly evaluated, but it doesn't apply everywhere. It doesn't generalize for very small scales, very high speeds, or very strong gravitational fields. So we need general relativity or quantum field theory or something like this. But the model is still useful, right? We can't say whether it's correct or not because we know that it's incorrect in some cases, but that's not useful. It's much more useful to figure out when it's useful. So when building production systems, we can't treat machine learning components just like any other components for which we have a specification. We kind of need to deal with them as unreliable components. So something that gives us the transcription, but we're not always perfectly sure that we can rely on the answer, right? We expect like a certain rate of errors, and we better design the rest of the system to be able to deal with those errors, right? Make sure that the self-driving car doesn't immediately crash because of a single wrong prediction. However, as software engineers, this is not the first time that we see bad specifications. Actually, in practice, we almost never have great specifications. Try to get students or your colleagues to write good specifications, right? Some organizations are more successful than others, but we often have missing or weak specifications, incorrect specifications. And we counter this with agile methods and with more communication. Often we do integration and system testing because we can't just trust unit testing. We test in production. And then when the systems are safety critical, we have a long history of building safe systems from unreliable components. Things like fallback strategies, mitigation strategies, right? Safety mechanisms in the system. And there's a long, long history of safety engineering, risk analysis, building mitigation strategies. It's just that these techniques are expensive. We teach them, and in safety critical domains like aviations and nuclear power plants and so on, people use those and justify the expense. In our everyday software, we probably don't see them quite as frequently, and maybe we should see this more frequently when we use machine learning. There are other problems, so other things that change. Machine learning really interacts with the environment. We hear a lot about fairness issues and feedback loops. For example, YouTube used to recommend conspiracy theory videos a lot, so they would recommend this way more frequently than other videos because the algorithm has figured out people who start watching conspiracy theory videos tend to watch another one and spend really go down a rabbit hole and spend a lot of time watching those. And from the algorithm's perspective, that's great, right? Lots of engagement. We predict things that people want to watch, and it steers people who haven't seen any conspiracy theory videos in this direction too. So what we're seeing here is the model makes a recommendation. In the real world, people pick up on that recommendation. They actually go down this rabbit hole. The algorithm observes this, sees that even more people follow this path, and comes back and it reinforces the algorithm and makes it even worse. And so there's really the environment and how it interacts with the machine learning components and the other parts of the system here, something that we reason about. But again, from a software engineering perspective, that's not terribly new. I mean, it's a big problem, but we have crashed software before. Like Lufthansa flight 2904, which crashed in Warsaw, is a common example that overshot the runway because the plane didn't brake. It didn't engage the reverse thrusters because the software didn't think that the plane was actually on the ground. There was aquaplaning and wind, so the sensors didn't work as expected. So there was some the state that the software thought the plane was in didn't match the reality, right? So the environment and the software state didn't align. And that caused big safety problems. Most safety issues are actually at this connection between the environment and software. And in software engineering research, there's often called as the word and the machine. Like, we really need to focus on how the environment interacts with the software. At the software level, we can think about specifications, but we can really only reason about sensor inputs and outputs. And then we need to make assumptions about what they mean about the real world. So this is a point where we really, really focus on requirements engineering. In a safety culture, this is really important, right? So we have mechanisms for doing this. It's just in lots of software projects we don't, and again, it's kind of expensive, and a lot of software engineers don't particularly enjoy doing requirements engineering work that much, right? Couple of more things. In machine learning, there's often not just one model, but multiple models. Like in a self-driving car, I've seen lots of architectures with 20, 30 models, and they all influence each other. And there's this idea that if one model changes, that kind of changes everything. So if I improve lane prediction in the system, it doesn't mean that the entire system quality improves. It could actually cause some weird interaction with steering planning, that steering planning previously compensated for weirdnesses and certain bugs in the lane prediction part, and now it doesn't work anymore. Right? So you kind of need to retrain this and evaluate the entire system. Unit testing becomes much more difficult. But again, also in software engineering, we have seen issues with composing subsystems and plugins that kind of interact in unanticipated ways. There's a huge research culture just around feature interactions. Lots of this happened early in the 90s on telephone systems, but a lot of this happened more. We realized how important software design is to plan for interactions, how system testing is important, not just unit testing, and so on. Last point that I'm just briefly going to make is data is important, and it's really big, maybe somewhat obvious, but also we had big data without machine learning, and there's a lot of infrastructure that we built over the years that we're now using much more in machine learning projects often, right? Distributed systems, stream and batch processing, Lambda architecture comes up a lot. So there's a lot of infrastructure and a lot of knowledge of how we can deal with a lot of these issues. So in general, my opinion in this world is that machine learning, there are a couple of things that kind of push us much further than we had before, but there's also a lot of existing techniques that we had in the community, in the software engineering community, that we can use to build those systems. A bunch of them are going to be expensive, right? So the machine learning systems that we often build, those are not the simple hobby projects or simple web applications. Those interact with the environments. A lot of them are safety critical or have some safety implications, right? They are much bigger in scale often. So they're really pushing the envelope in system complexity. So my hypothesis in this area is that in the past, we often got away with kind of shoddy, kind of poor development practices, but with machine learning, we will often not, because we're trying to build much more complex systems, and suddenly things like safety and requirements engineering and all the risk analysis becomes suddenly much, much more important in a lot of these systems. So let me switch gears a little bit. I want to pitch why it's so important to think about the entire system and not just on the model. I could have picked many stories, but I picked quality assurance, how we test systems, just as an example of how there are many different views to view testing, and whether you look at the model or at the system, this will change drastically. And I want to walk you through from the model to the system, just with this single example. And we could have done the similar things with requirements engineering or architecture and things like this too. So you often see diagrams, something like this, describing how machine learning or how data scientists build models, right? Start with some model requirements, collect some data, clean the data, label the data, do some feature engineering, training the model, evaluating this. And then this is terribly iterative, right? Because the first model doesn't work, you improve things, you may need to collect more data, engineer more features. It's very explorative, very scientific or science-like. And there are lots of these models. You may have seen CRISP-DM as a process model, also emphasizing the iterative nature, but let's stick with this. In a typical machine learning course, as I mentioned before, focuses pretty much on, here's a data set, do some feature engineering, evaluate accuracy on a model that you trained, and you're done. But even here, there's a lot of, we can already think about how do we evaluate these things. And the traditional approach here is model accuracy. In the machine learning community, confusingly, this is called performance, which as a software engineer, I associate with latency or some timing related issues. There are lots of these words that have kind of different meanings in different communities, but let's stick with this, right? So this is model accuracy. Typically you have some test data and you see how well does it do on the test data, right? How, of these cases that I know have cancer in the image, how many of those do I detect? How many false positives do I have? And there's a huge amount of discussion. So typically you would train a classifier, evaluate it, right? You've done your homework. You can push this further. So data scientists really start thinking about true positives, true negatives. There's certain kind of mistakes that are more important than others, right? Accuracy, recall, precision, area under the curve, all these kind of things. And then Nicholas actually talked about some things where you think much more systematically about what test data do I use. Not all test data is equal. I think there's a lot of things that match very well with traditional software testing, black box testing, like boundary value analysis, equivalence class testing. All of these things can provide some inspirations, maybe thinking about some capabilities that the model should have. But really, this is a focus on accuracy on some sample data. So you can't really, you don't necessarily have a lot of confidence of how this is a unit evaluation, right? We can also evaluate, automate all this evaluation. This is a very straightforward step. Software engineers do this all the time, right? Automate unit tests. We have a lot of infrastructure for doing this with machine learning to automate. Like every time we train a new model, it does all these evaluations. It plots nice results, things like this. But already here, we can start thinking about, even if we just care about the model, there are a couple of other qualities that we might worry about that are not just accuracy of the predictions. We might care about how long does it take to make a prediction. If we're using this in a real-time environment of a self-driving car, we have a few milliseconds to make a prediction because then the next camera image is coming in. So there's actually hard requirements. Also, if you run this at Microsoft scale in the cloud and you have millions and millions of users, how easy can you scale these things? How quickly can you make a recommendation for Netflix, right? Users are not willing to wait a minute. What's the cost associated with this? How big are the models? Can you deploy them on a smartphone, right? People start caring about fairness, robustness, a couple of safety, security, and privacy properties, explainability, reproducibility. So there are more qualities than just accuracy, and a lot of them we can already measure at the model level. Right, so if we look at our transcription service again, we care about accuracy of the model, but we also don't want the transcription to take a week, right? We want relatively fast turnaround of our transcriptions for MP3 files. We might even want to do live transcriptions of conference talks or videos, TV, things like this. But that's just the model, right? We also care about deploying the model and then updating the model. So this is where you actually see extra steps in this pipeline, and we start thinking of this as an entire pipeline that's actually reproducible, right? So we have a deployment phase, we have a monitoring phase. A lot of these final areas here are typically, there's a lot of focus on automation under the umbrella MLOps these days, right? So kind of automating this, automate deployment, tools for monitoring and so on. There's a lot of infrastructure for scaling, training and deployment really at a massive scale at the cloud, but also infrastructure to just make this entire process repeatable. So when data changes, we can easily deploy a new model. You may have seen this figure before, this from Google, describing that model code, the machine learning code, the TensorFlow code that you're writing or scikit-learn code that you're writing, that's actually a tiny amount of code compared to all the code that you write for data collection, for feature engineering, for model serving, for monitoring, for managing cloud resources, and all these kind of things, right? So if you actually want to deploy a model into production, there's so much more stuff out there that you need to do, right? And actually, if you talk to big companies, they often have massive teams just to do the serving infrastructure, just to scale this, and works with a cloud team and so on. Today, a lot of these boxes are shrinking. So this picture is now 6 years old. A lot of these boxes are shrinking because we standardize a bunch of these tools. Like if you do TensorFlow, you can use TensorFlow serving to deploy a model in the cloud with like 3 lines of configuration, like a shell command, right? You don't write your own massive infrastructure anymore. There's a lot of tooling out there to automate a lot of these, but still there's a lot of knowledge out there and a lot of things that you need to configure and maintain to build these pipelines. And this is really dangerous that there can be silent mistakes. So things that I've heard companies complaining about is they are training a model every day and they are uploading the model to their inference server, to their serving infrastructure every day. And something went wrong. The model became too big and the upload failed and nobody got notified. And they only realized like a month later that they're running with a really old model in production, even though they had improved things, and with data drift, they have updated things and so on. And so what you want to avoid are silent mistakes where some steps in the pipeline simply break. And this is again where we can come back to quality assurance and testing, because it's really important to think about how can we test the entire pipeline. And you can test everything in here. This is again, a picture from Google, but you can test the infrastructure. We talked about testing models, data tests, monitoring. You can test the monitoring infrastructure with some fire drills or chaos engineering, where you kind of in production try to see, if I take the system down, do I actually get a notification, right? This is where testing error recovery behavior becomes really important. Testing with stubs, for example, so you artificially in a unit test inject a failure or pretend that the network connection fails, and you test whether your retry mechanism works. Right? So there's a lot of testing that can also go into the infrastructure, not just the model, but also how we deploy the model, that our updates work, that our monitoring works, and so on. Right? So for a transcription service like this, we might need to update our models every couple of months or so, and we want to automate that process. We don't want to have too much that can go wrong by manually copying files around and so on, right? This is really where pipeline infrastructure, building the infrastructure, and testing it helps. But again, we're still at the model, right? We're now in a stage that might be called ML engineering, where it's about having a model and deploying the model, and the model is one component in the system that we can use as an API that's really scalable. But we ignore the rest of the system, right? I showed you this one before as all these great components that are the rest of the system beyond the speech recognition, and everything that we just talked about, the whole ML engineering part is just there to build this one component or these components in the monitoring infrastructure. But we really also need to think about the rest of the system here. And that's actually something that's often ignored. And this is often where if we just build the model and then think we can wrap a little bit of infrastructure around it, we often run into problems. Right? So it's actually really hard to design the right system around a model. There has been a lot of research, as I mentioned, on cancer prognosis, detecting whether there's cancer in an image. But when people try to get radiologists, practitioners to actually use it, they don't get very far often. And there have been studies trying to figure out why. First of all, practitioners don't like to be replaced, right? So there's a framing issue here that you want to support a practitioner like a radiologist, make their job easier, but not necessarily replace them. Although maybe we should replace some of them and make this more accessible. But there are much more severe issues here. One thing that they have observed, for example, is that the cases where it's hard to detect this is if somebody comes into an emergency room and we need a prognosis right now. In those cases, we often only have partial information. We don't have the full patient records, things like this. And those are things that the machine learning models are usually not well trained for. We trained them for the wrong problems. We trained them for the easy problems, not the problems that actually occurred in practice. Another thing that people have studied is that practitioners, if they want to trust those systems, they need to understand, at least to some degree, how they work. They need some explanations, and not just explanations of a single prediction, right? Not just, oh, here's maybe cancer in this part of the image, and this looks fine. No, they want to know much more. They want to know, how was the model trained? What data was it trained on? Can it actually, does it perform equally well on different men and women, for example? What kind of information does the model use? Does it use patient records? Does it use anything that I don't have access to? How aggressive is it in this prediction? More like this colleague or that colleague, right? Radiologists are known to be more or less aggressive when they're making these, or conservative when they're making predictions. So there's a lot of information here that goes into actually designing the right user interface, the right interaction, and then based on this, figuring out what kind of model do we really need to support that task. For example, explainability is really important. Maybe some of the deep neural network architectures are not the right place because we have a really hard time explaining them right now. We're getting better with some techniques to approximate some of this, but it's a process. Safety is another issue. This is my favorite example of a smart toaster here. So imagine a toaster with a machine learning component that detects or that predicts how long should I toast something to always get the perfect bread or whatever I put in there. And the machine learning component will not always be perfect, right? It will be maybe 95% accurate, and it will often give you great toast, sometimes under toasted, sometimes over toasted. But what I want to avoid is, it can occasionally burn my toast, but it should not burn down my kitchen. Right? So it should not continue toasting something for hours on end. So how do we do that? We could improve the model, right? Kind of figure out more error cases, get more training data, make sure that the model is more and more accurate. But again, as Niklas says, there's a long tail, right? There might be always some cases where the model still makes mispredictions and we don't really understand why. And at some point we need to step away from the model. The model is not unsafe. What the system does with the environment, the actuators turning on the heat, that's what's potentially unsafe. But it's something that the model does with this, well, what the system does with the environment. So there are a couple of safety mechanisms that we can build in outside the model. We can just set a maximum toasting time, right? We don't even need to tell the model. If it predicts something higher than 5 minutes, we just max out at 5 minutes. We can put in another temperature sensor, and if it goes too high, we should just shut down. We don't even ask the model. Or we go the hardware route and put in a thermal fuse, a really cheap device that just, if it overheats, it cuts down the power, right? It's just a fuse in there, and it will prevent us from burning down the kitchen, right? So what we're talking about here are risk mitigation strategies that happen outside the model, and to do them, we need to think about the entire system, not just the model, right? The model may make wrong prediction. It's an unreliable component from the perspective of safety, but we can think about how can we make the entire system safe and how the system interacts with the environment. The last point here is that the model goals, like optimizing for accuracy or maybe fairness, latency, or training costs, is not necessarily the same as a system goal, right? With a system, we typically have a goal. We want to maximize sales mostly, right? Make some money, maybe improve the environment, and maximize engagement time, which again leads to money in the end. And hopefully a better model will support our system goals. But that's not always the case, and not only the only point of how we can achieve this. There's a nice example from Booking.com who they build like hundreds of models to predict, like, are you traveling alone with your family? Are you flexible about your dates, to recommend different hotels to you? And what they're interested in is not really the accuracy of their models. I mean, that's a better accurate models helps them to make better recommendations, hopefully. What they're interested in is selling more hotel rooms. And they ran experiments where they actually saw, when we improved some of the models, this is where you want to be. So the model improved accuracy of the model, and they sold more hotel rooms. So the conversion rate, how many people actually bought something in the end, improved. But they also saw cases where they improved the model and they actually sold fewer hotel rooms, right? So model accuracy improved, but the system goal actually didn't. They speculate a lot about different reasons. One reason that I like, which I'm not sure is the right reason here, they talk about an uncanny valley effect, where if the website gets too good at predicting how you're traveling, it becomes kind of creepy. I haven't told them that I'm going to travel with my family and they recommends me this family hotel, right? So this creepiness might be something where a better model is maybe actually not helping with the system goals. If we think about the transcription service, if we improved transcription accuracy a little bit, let's say from 95 to 96%, great. But I bet my customers would prefer it if I lower my prices, like if I can run this faster, if I give them faster time, they might not even notice the 1% accuracy difference, right? Accuracy is not the only quality that we care about in the system, and we should really think about what do we care about, what do our customers care about, and how do we foster the system goals, not just the model goals? And this is where we really almost always want to test in production, right? Production data is the ultimate unseen data. We can often approximate model accuracy, but we can definitely measure system goals. We can also test in production, like you've probably seen A/B testing, things like this, right? So if we have the cancer prediction system, we can observe, are the radiologists, the practitioners actually using the output? Are they actually looking at the results? How often are they agreeing or disagreeing with the output? And we can observe in production how well we're doing, right? Not just how well the model actually works for the images that we had as test data, but in production, how well the thing is doing. And we really need to design telemetry for this. How can we figure out in production, get information back of how we're doing? How can we identify mistakes in production? How can we get feedback without being intrusive? How can we see how the system is fostering its goals in production? There are lots of different ways. We can just ask users. We can ask them to complain if problems occur. The complaining part is we only get negative feedback, but that might be good enough. We might have some people that we look at results, right? So in the cancer prognosis case, maybe we have some specialists that look at the sample of production data and try to agree or disagree with the model. In some cases, we can just wait. If we're predicting prices for next week, we can just wait a week to see how we're doing next week. So there's really lots of design challenges around how do we build these systems, how do we design them, how do we get telemetry that we can actually evaluate things in production. And this is the last time I think I want to talk about this transcription service, because here's something, well, first of all, there's this, at the bottom here, you see the star rating thing, right? Simple enough. But one thing, and I don't know whether they actually use that, but it's really interesting. They provide a great user interface. Traditionally, when I did transcriptions, I would copy the text, or they would send me a text file. I would copy this into Word, and then you typically need to fix things. Here, you can click into a specific place in the text, and it jumps to the same place in the audio, and I can press play and listen from this place on. I can go back. I can jump back and forth. It shows me when it's uncertain about those words, maybe show me some alternatives. And all of this keeps me in the editor, right? So I don't copy this to Word. It actually is much better to edit this in the cloud infrastructure, in their editor, in their website, that doing this offline. Because of this, they actually could see whenever I'm changing a word, if it's misspelled and I'm changing it, they could get really fine-grained telemetry and identify what has changed. So what I'm trying to get at here is that there's a real connection between how we design the user interface and how we can evaluate the system, right? Thinking about the entire system and about the design, in this case, the user interface, enables completely different ways that we couldn't evaluate this if we only thought about the model. There are lots of challenges still. For example, you might not want to collect your customer data because of privacy reasons. You often deal with massive amounts of data. But I think what I've tried to show you here is that there are model concerns, but really you also want to think about the system. There's a lot of requirements engineering and user interface design that's important to think about what are really the qualities that you care about and evaluate them in all stages. Evaluate the model, evaluate the pipeline, evaluate the system, design telemetry. So I hope I've convinced you that you really want to think about the system, about the entire infrastructure here. And just briefly at the end, I want to briefly wrap up by talking about how do we do this if we have these complicated systems and we need all those people, right? We have data scientists and software engineers that are kind of apart in their education. What we really want is we want to bring them together, make them work together. Traditionally, you might see people who talk about unicorns. Those are the rare people, mythical people that can do everything. They are experts in data science, they're expert software engineers, they have the domain expertise, right? So they can do all the hard model building part and deploy it and build the system around it and actually understand cancer in the way, right, or transcription. Those are rare and really expensive to hire and to keep, even if they exist. A much better strategy to think about is to hire interdisciplinary teams of T-shaped people. The idea here is that you don't just want somebody who's I-shaped, who has deep expertise in one thing, who can build great machine learning models, but nothing else, or who can design web page front ends, but doesn't understand machine learning or any other constraints. You also don't just want generalists, may I say managers, people that kind of can talk to everybody, but don't necessarily have domain expertise in any area. What you really want is somebody who's an expert in an area, who has enough of an understanding of the concerns of other people that they can talk to them, right? So for example, you want a data scientist who knows about possible concerns in the user interface and how they might be affected so that they can talk to the user interface designer, talk to them and ask them, what kind of explainability do you need? That can figure out a joint language that are not confused if they talk about performance and mean something else when I talk about performance. Right? Same, you want software engineers that have some appreciation of data science so that they are not completely confused if they are trying to write tests and they don't get a specification or things like this. Right? That they can actually understand and talk to each other. We've talked to a lot of companies recently trying to figure out where collaboration problems are, and I don't want to go deep into this. One thing that we found is that pretty much every company is different and has different structures. Almost always you want some sort of product team and some sort of model team, but you don't want them siloed. If you silo them, if you have the data scientists in one group and they don't talk to the software engineers in another group, at some point that software engineers get a notebook and they're frustrated with it. They're frustrated with code quality. They don't understand it. They re-implement it, lose most of the benefits. Or you work with an external operations team, lots and lots of communication problems that we see all the time. The things that work better is if you actually have communication bridges. So the really divide and conquer strategy doesn't seem to work very well. You really want to foster communication. We have seen rotation approaches where software engineers join the model team for a while and the other way around, where you have contact points in the teams, where you have joint responsibilities. Those tend to work much better. Mixed teams. A lot of big companies hire actually lots of software engineers in the model team to do a lot of the engineering in the pipeline infrastructure. And so you really, and for doing this well, you want T-shaped people. The vision here, I'm going to bring DevOps up again. At least my vision is that we can learn from DevOps. DevOps was addressing a somewhat similar problems where we had developers and operators that were kind of at odds with each other. Again, different backgrounds, different responsibilities. The developers didn't really care about deployment and had lots of, and operators had lots of problems of setting up updates and things like this. And there was frustration back and forth. But what DevOps did is it brought those together, gave people joint responsibilities, joint tools, joint language. So developers would, for example, put some of their stuff into containers, make it easier for operators. The operators would give developers some telemetry data, some monitoring infrastructure, and much faster feedback, faster releases. So both sides kind of benefited, and they worked much closer together. We broke up the silos. We have a clean infrastructure, and I hope we get to something similar between software engineers and data scientists, where they actually work much closer together. But I think we have some way to go. What we want is interdisciplinary teams with joint responsibilities, joint vocabularies, joint tools, where people, all of them, appreciate some system thinking, are aware of production quality concerns, not just of model accuracy, and where we get into a culture of doing risk and hazard analysis, especially for systems that interact, which are pretty much all of them that interact with the real world. So we really want to bring them together. There's a lot to go here, and I'm running out of time. If you're interested in any of this, I've been teaching a class and the material is online. I've also been writing about this and starting to write textbook and releasing chapters one by one. If you want something right now, I can recommend this book. This is the closest that I've seen, Jeff Holton's Building Intelligent Systems, to really think about not just the model, but how it fits into the system. And with this, I'm going to wrap up. Right, so I wanted to show you what it really takes, in my view, to move machine learning projects into production. And you really need interdisciplinary teams. A lot of problems come from people with different backgrounds. You want data scientists and software engineers and all other roles to work together here. You really want to focus on the entire system, not just the model. I've shown you this with teams. That's all I have. Thanks for coming and having me. And I can answer some questions if you have some.
Yeah, first, thank you very much, Christian. Christian, questions, English or German?
Either way, I can try.
Okay, also noch immer Fragen in Deutsch oder Englisch. Gibt es direkt welche aus dem Raum? Ja.
I've seen in the last time in some projects some people you would call I-shaped people. I have the feeling they were not in industry, but more in academics. Without complaining about them, because all did their job good, the overlap between, as you explained, you really spoke to my heart, didn't work at that point, and I was missing that. Do you have any idea how to start building T-shaped people might be even earlier without overloading, let's say, our courses?
Yeah, I'm an academic, so my answer is always education, right? But maybe you have a chance of hiring T-shaped people, one or two of them that can act as a bridge in a team, right? Maybe not everybody is this, but you have somebody who can speak for the team. I'm not sure. You can educate people on the job. My impression is, and again, I might offend some data scientists here, but my impression is that it's easier to teach a software engineer some data science to understand the language, and they're interested anyway, than to teach a data scientist some software engineering. So maybe you can have some software engineers with interest in data science work as a bridge, work on those teams. But I don't have a great answer.
Actually, I have a follow-up question going in the same direction, probably because we are having similar background. If we talk about teaching, what I see, and I'm not sure whether the situation in the US is the same, that we are seeing more and more specialized programs instead of generic computer science education and then specialization on top. I'm wondering whether that's actually a basis for making the problem in the future even more prominent, and whether it would be a good idea to have it the other way around and say there's some more enforced commonality and then you can branch out. Or do you think it might be unrealistic? I don't know.
I mean, this is a big challenge in curriculum design. How do you allocate scarce time, right? And you want specialists. You want the vertical part in the T2, right? You want somebody who actually goes deep into data science. And I don't think they need to take the full curriculum on software engineering that our master students in software engineering would do, right? But I think we want to make them somewhat sensitive. So I would hope that maybe a data science course could actually have students put something, actually deploy a model in some form, right? We run this in our course in simulation where students actually have 800 milliseconds to make a movie recommendation, and they're shocked that how little time 800 milliseconds is for a lot of their models. It seems really generous to me, but to them, they have the initial models take something like a minute to compute the ranking, right? Just expose them to some of this, expose them to some of the risk analysis. A lot of data science courses now start talking about fairness. I think that's a good bridge to talk about requirements engineering and more broadly the system, not just the model. So I think we can put some of the content in there, but I think it's on the people who design the curriculum that, so our course on software engineering for machine learning is actually in the curriculum of the data science master's program too. So the people who run the CMU computational data program, I forgot the right name, approached us because they wanted some engineering component, right? And we don't teach all of software engineering, and we don't expect that they will be great at unit testing or things like this afterward, or software architecture, but they've heard it before, and they can talk to somebody and maybe appreciate the concerns. And I would hope that we can do this in both directions, right? So also with the software engineering specializations, that we teach them a little bit about machine learning, right? Maybe not a full course, maybe just a part in a larger course. But yeah, it's hard. It's you don't have a lot of time and a lot of material.
What question? Then perhaps follow-up one. I was thinking, as you presented a lot, or you also introduced a lot, the aspect of user interfaces, and we saw that with the final system. And my impression is, just as you said, that very often getting the right data is part of how you design the whole user experience. And we are now talking a lot about this interaction between software engineers on the one hand and machine learning on the other hand. But I was wondering whether there's actually, or there shouldn't be, somebody who is currently mostly overlooked, the UX or UI persons, and having them, and actually the problem would be then even more difficult. But wouldn't it be better if all three of them would seen as an interdisciplinary team?
Yes. It depends a lot on where you draw the line, and I want to keep it simple for the talk. So where's the line between human-computer interaction and software engineering, right? So this overlaps a lot in the requirements area and design area. But yes, there are certain specialties that a user interface engineer has. And to be honest, I think the most interesting papers these days about system-level machine learning considerations appear in the human-computer interaction communities. So they actually care about the system. They care about how to integrate fairness into a system, not just in the model, right? How to design systems that are understandable, and how does system design influence what kind of model we need. And I wish we software engineers were a little bit more louder in that community, but I think we're getting there eventually. But I think right now, maybe I should have relabeled this as user interface designers, but you also need people who do the safety analysis and things like this, which are probably not the user interface people alone. So yeah, all three of them, and probably bring in lawyers too, right? Bring the operators in, bring everybody in.
So it's a full
maybe
room problem.
manager.
Right, thank you. I don't see any open questions right now from the audience. It's also, let's have a look at the watch. It's also a little bit late now. Let's say we do now a very short break, so everybody, gib wieder auf Deutsch. Machen wir eine kurze Pause, kann sich jeder einen Kaffee holen. Es war eigentlich eine Viertelstunde Pause eingeplant. Das sollten wir vielleicht nicht ausreizen und dann direkt in knapp 5 Minuten oder so das Panel anschließen, sodass das nicht zu lange wird heute. Ja, also ganz kurz, Kaffeebar stürmen und dann wieder zurück.